All right. So this is my torque and angular momentum major assessment. So I chose question 1 for this. So it asks, which force exerts the smallest value of torque? So, and I said force number 1 exerts the smallest value of torque because it is not pushing at all on the rod because it is behind the pivot point and center of mass. So, and when it turns, it's not exerting much of a force. And then we go down to number 4, and it asks if the rod was free to rotate, in which direction, if any, would it rotate? And I said it would rotate clockwise because the pivot point is not directly in the middle of the rod. So the center of mass is going to be further right than where the pivot point is, making the rod have more weight to the right, forcing it to go left and moving clockwise. And then we move to question 6, and it asks, explain what needs to be done to balance the seesaw with the girl on the left and the apple on the right. And so I wrote, the girl needs to be closer to the center of the seesaw, and the apple needs to be at the very end of the seesaw. And this would make the center of mass be more equal and would level out the seesaw. Okay, so then we move to question 7, and it asks, for the situation shown on the left, the rod has a pin through it so that it's free to rotate. A 35 Newton hanging weight is hung from a rod at a distance of 12 meters from the pivot point of the rod. What weight must be hung a distance of 8 meters from the pivot to balance the rod? So first, we do one of our angular momentum equations. So we find the force. And so from the question, we see that it has 35 Newton hanging weight and with 12 meters of distance in between it. And so both weights are pushing down, making the left side be greater. And so when we plug everything into our equation, we get that the gravitational force is going to be 52.5 newtons. And for B, it asks how much upward force does the pin have to provide so that the rod does not move. And so I wrote that it needs 87.5 newtons of force. And what I did there was I took the 35 newtons and added the gravitational force, which is 52.5 newtons, and I got 87.5 newtons. Okay, so for question 9, a steel rod asks, a steel rod is attached to a wall with a pin through the center. The steel rod is free to rotate. A 3 kilogram mass is hung on the left side of the pivot at a distance of 0.6 meters from the pivot. A 10 kilogram mass a 10 kilogram mass is hung from the rod on the left side 0.3 meters from the pivot. A student only has 14 kilogram mass and is trying to balance the rod. And then it asks what distance from the pivot should the student hang the mass so the rod does not rotate. So we get another one of our angular momentum equations. And so we put in the we put in all the things it gives us here, like the 10 kilogram mass, 0.3 meters from the pivot point, and plug it into our equation. And basically, we add the two sides together, and it gives us a forgot the word for it, but R equals 0.34 meters. And
the R is the distance from the pivot point.
Okay. And then so for B, it asks if the steel rod has a mass of 5 kilograms, what value of the upward force must the pin provide to keep the rod in equilibrium? And so we draw a diagram here. And so basically it's showing all of the forces here, and they're all going down because they're hanging. And so we basically just add up all of our forces and we get 230 newtons. So that is it for question 9. So then we move on to question 14. And so we use one of our last angular momentum equations, and the question's talking about a 25 kilogram child sitting on the outermost edge of a merry-go-round, and its rotational inertia is 275 kilogram meters squared. And so it's just asking us what is the total rotational inertia of the child and the merry-go-round. And so we take our equation and we plug in what we need. And so radius is squared because it's gonna double in our equation. And so we fill that out and we add them together and get 500 kilogram meters squared. And then so question B asks, the child now moves towards the center and is only 0.5 meters from the center of the merry-go-round. What is the new rotational inertia of the child in the merry-go-round? So child is going to be moving at a slower rate basically around the merry-go-round. So we basically plug in how far away he is from the center of the merry-go-round, and we basically add all of it up, and we get 431.25 kilogram meters squared, which is going to be our answer for B. And then for the last C, it asks if the child and merry-go-round were initially rotating at 6.28 rad per second when the child was on the outermost edge of the merry-go-round, what is the rate of rotation when the child moves to 0.5 from the center? 0.5 meters. So we use this last angular momentum equation, and so we plug in the 500 kilogram meters squared, and then we plug in 6.28 radius radians per second. And so basically that's gonna show us the force of the inertia, and it's gonna give us 7.28 rod per second, radians per second. So that is my explanation of torque and angular momentum major assessment. Thank you.